Okay, so time to get started. Let's start moving along. Okay, so new topic today. We're going to talk about dot products. Talk about dot products now. So this is section 12.2. I want to say. Pretty sure. Anyway, so it addresses the question of how should we multiply vectors, and I emphasize this word "should." Right, so don't think of this as it's etched in stone somewhere that the multiplication by definition means this for no apparent reason, and that's just how it is. Hope it works out for you. Right, that's not what's going on here. We want to hopefully come up with a choice, a good choice that gives us an operation that actually makes sense, that allows us to use vectors to connect it to things that we need to do, things that we want to understand. Right. Okay, so that's a hard question to motivate, why we should multiply vectors a certain way. So what I'm going to do is I'm going to show you two good answers. By the way, that's a weird thing. It turns out there's two good answers to this question. We're going to have two kinds of products that both, as it turns out, will naturally connect to important geometric ideas. It's counterintuitive, but it is. Okay, so we're going to take these one at a time. The first one I'm going to tell you about is called the dot product. I cannot emphasize enough. You have to call it the dot product. You cannot just call it the product. You cannot just say, I'm going to multiply these two vectors. That's non-specific. Which one do you mean? Right? Okay. So here's the definition, at least in R3. If you have two vectors in R3, we denote the dot product with this formula. I think the name makes sense with the notation, right? That's why they call it a dot product. And the definition is the dot product is this formula. It's very weird looking. It looks sort of too simple to possibly be useful. Why are we adding these products in there? That seems strange, doesn't it? Anyway, yeah, it's pretty counterintuitive. Non-intuitive, maybe is a better word, but that's the definition, and it turns out, for reasons that will become clear over the next couple of pages, it turns out this is a really useful definition, despite not looking like it. Okay. Quick final reminder, make sure to put the dot in there. Some students are just a little too sloppy with notation, a little bit too casual, and decide, I'm just going to write VW. So that's a thing. And of course, in regular algebra, if you want to note A times B, you can just write AB, and that means A times B, right? Not with vectors. If you write VW, I don't know what that means. That's not a thing. So please don't do that. Yes?
So when you get the dot product of those two vectors, the result is not itself a vector?
Weird, isn't it? That's exactly right. So that's a good catch. So this is a vector, V is a vector, W is a vector, and yet the product of those two vectors is, good catch, that is a single number, right? That's a scalar. It's not a vector. And that's strange. Nevertheless, it's going to turn out that this is geometrically very natural. Okay, all right, so what can we do with this? First thing I want to talk about are some algebraic properties. Now keep in mind, this is a brand new operation, dot product, that we're defining. We're using a familiar notation. That dot is sometimes used in algebra to mean times, right? So it's familiar notation. We're calling it a product. That sounds familiar. It's a familiar word. Right? But that does not mean that, just because it cosmetically, we've made some aesthetic choices that smack of multiplication from algebra, that it has to behave algebraically like our old friend multiplication from algebra. Far from obvious. Nevertheless, here are some true facts that you can check. So this is part of why we call it a product, because it behaves like a product. Okay. All right. So these deserve to be checked. I like previous algebraic properties we've talked about, I suggest you pick a couple of them. Work them out by, from the coordinates of the vectors. It's easy to show. I like to point out at this time a reasonable question to ask. Again, I pulled this definition of dot product kind of out of a hat, and we've seen now that it has some nice properties. And roughly speaking, the question I want to ask is, are you impressed yet? And I pose that no, you shouldn't be. Please don't be impressed. that I found a formula that satisfies these three properties. I mean, it's good news, but turns out there's lots of formulas that you can write down that satisfy these properties, and they're not geometrically meaningful at all. All right, so here's an easy example. If you just scratch off, do like that. This formula satisfies all of these properties, right? And it's not geometrically meaningful at all. So we need more to be before we're actually impressed. Here's one. Now this starts to get a little bit impressive. Dot product of vector with itself, and you get length squared. And the reason I suggest you should be slightly impressed here is length is a geometric concept, right? So what we have here is we've made an algebraic choice that connects to, in a way, a pre-existing geometric thing. I don't know if impressed is the right word, but at least it's an eyebrow raiser, right? It's, oh, okay, well, maybe this is going to go somewhere actually useful. Okay. Not too impressive, though. Here's the next one. This is called the Cauchy-Schwarz inequality. And this one's a lot more impressive, I think. Now, the disappointment of the Cauchy-Schwarz inequality is that it's an inequality, right? I mean, we're not saying what the dot product actually is here. Nevertheless, it's pretty hard to figure. If there's not something natural going on here, how could the product of two lengths so consistently relate to this dot product? I mean, it's not precise, but it is consistent. Well, that's kind of neato in a way. By the way, this formula here is interesting in a couple of ways. This gets a name not because this formula, as I've written it, is super powerful, but because there's a generalized version of this. If y'all take Math 216, I'm going to show you in Math 216 the general version of the Cauchy-Schwarz inequality. Give me 2 seconds. In the general version of the Cauchy-Schwarz inequality, we define a generalization of the dot product in a shockingly broad array of circumstances, and that generalization has this same property. Yeah.
The dot product is scalar, so what
yes.
is the absolute value? So we'll just say it's not negative.
Yeah, this is just plain old absolute value from. Yep. It just means throw away the minus sign if there is one. Yep. Totally. Yep.
Related question.
Yeah.
Basically, when you have the double lines on either side of the V, is that pronounced just the length of V, or is that the absolute value of the length?
Yeah. No, that's so. I like the double lines to emphasize that this is a length, or sometimes we call it a magnitude of the vector. Some books very plausibly and reasonably use single lines. I just like the cosmetic difference. Yeah.
Okay, so there's no difference, like algebraically speaking, if you have one line versus two lines.
Well, the difference is, so the single line looks like an absolute value. You can't talk about the absolute value of a vector. You can talk about the magnitude of a vector, and we can use the same notation for it, but it is a new construction called magnitude, right, or length, right? The double line is just using a distinct notation for what is kind of a distinct thing, and it's not important. Some people use the single lines. It's fine. It's not a problem. There's no situation where, a confusion arises because of the shared notations, and therefore someone gets a wrong answer. That'll never happen. But I don't know. Cosmetically, I just kind of like it.
Okay,
yeah.
Thanks.
Yeah. Okay. So, in Math 216, we're going to see a much stronger, broader version of this. The other thing I'll tell you about the Cauchy-Schwarz inequality is it's actually hard to prove in that general context. Right? It's going to be easy to prove here in Math 212, but it's hard to prove in more general terms. I say hard; it's harder. Here's the one that's going to look like it's the most powerful here in Math 212 context. This is a general formula, all dot products, not just a dot product of a vector with itself. It's an equality, not an inequality. This is a very strong statement, and look at this formula, this dot product that we define. Give me a second. That's defined purely algebraic definition, right? this formula that I'm saying it's equal to on the right is length, which is intrinsically geometric, another length, and an angle, which angle is another just naturally geometric kind of a thing, right? So this is a extremely strong connection. Oh, my thing didn't work. Extremely strong connection between algebra and geometry. Yeah.
Is that not proof though of the thing about it?
Yeah, you can use it for that. Yeah, of course we haven't proved this yet either.
Right, but if you could prove
Yes,
that,
and I'm going to make that observation in a couple.
it's the cosine.
I'm going to talk about that a little bit later. Yeah, absolutely. Okay. All right. Okay, so this one I think you should be impressed. Right? Now all of a sudden, this seemingly weird and arbitrary formula that I just wrote down, come on, you're just going to multiply the coordinates and then for no apparent reason just add them together? Here's why. That's amazing. Right? That's something that's such a disconnect. This again is defined in purely algebraic terms, and this is all geometry. Okay. All right, by the way, this angle, theta, is the angle between the two vectors. Okay, so let's prove this formula. This is one of the rare uses of the law of cosines. Do y'all remember the law of cosines from way back when? Okay, so here it is. Law of cosines. If I were to draw these two vectors, if I were to complete that into a triangle, right, where that third vector is the difference, v minus w, right? Altogether, then the law of cosines, in reference to this angle there, the law of cosines says that. If you're a little shaky on your high school geometry, you got to go back and take a quick look. The law of cosines comes up every now and then, but when it does, it's really, really, really useful. Okay. All right. Now here's another thing, though. Let's look at this. V minus w magnitude squared. Don't forget this formula that we've observed already. We already know this is true. Easily proved. Easy to prove. A magnitude squared is a dot product of that vector with itself. Well, that means that it's v minus w dot v minus w, and then you can just FOIL that out to turn it into this. So altogether then, now of course I've computed the same thing twice, therefore these two results are equal to each other. I take this fact, cancel out the common terms there and the common terms there, and then cancel off this common remaining factor of -2, and look what you got. We have now proved v dot w is what it's supposed to be. So it's a lovely little argument. Thank you, law of cosines. Right, and anyway, so we're done. Okay, and then as you observed earlier, take this equation, take the absolute value of both sides, and you get the Cauchy-Schwarz inequality. That's right. Okay. By the way, good exercise. Use this formula to prove the Cauchy-Schwarz inequality. Right? Again, by taking the absolute value of both sides. It's one thing to I can kind of see how that works, right? But here's what you're going to find surprisingly non-trivial. How to take that and write it down so that it is clearly, so you're communicating clearly to your reader, aka your grader, right? What your point is. And it's really easy to write that down in a way where you find yourself, didn't I just kind of prove it backwards? Or can you do that? Is that legal? Anyway, it's not ultimately hard to do. It's just a matter of this is a kind of, you got to straighten out your thinking on how to write that down. Just get that straightened out so that on an exam you can just write it down. All right. Okay, so real quick application. Suppose you want to know the angle between these two vectors. And, at a glance, if you were to take a sort of a high school geometry point of view on this, it's like, well, these are two kind of random vectors pointing different directions. And you could, maybe try to find both of these angles. But then there's no Pythagorean theorem for angles. And this is a hard problem from a high school geometry point of view. But it's an easy problem from a dot products point of view because you can just solve for theta in that formula, right? Note that the dot product is easy to compute. These magnitudes are easy to compute. And it's just kind of arithmetic then. right? And you're left having solved for that angle just fine and dandy. While I'm here, quick observation: if you come up with an answer to a question, and if the answer is arc cosine of something, if it's not going to be a standard angle, just leave it as arc cosine of whatever, right? Please don't pull out a calculator and the calculator will then, come up with what we call a decimal approximation and then replace this exact correct answer with a close approximation, aka wrong answer, right? So we want exact answers in math classes unless it specifically indicates, give me a number, give me a decimal approximation. Okay, related and sort of an immediate consequence. Let's see. Let me got to zoom out a notch. This formula. Think through what happens if you have non-zero vectors. So neither of these is zero. The dot product, whether it's positive or negative or zero, corresponds perfectly to whether the cosine is positive, negative, or zero. And cosines being positive, negative, or zero to tell you immediately whether the angle is acute, obtuse, or a right angle. Yeah. So neat fact, the dot product is a real quick way to at a glance decide if an angle between two vectors is acute or obtuse or right. And a very useful specific example of this is this last one here. Being able to identify when angles are right angles. Really important. We're going to see a lot of that pretty soon in the class. Okay. All right. Now there's a sticky point on this, and that is if the dot product is zero, I still have to confirm that the vectors are non-zero vectors before I go around drawing conclusions, right? I mean, I can't, just because a dot product is zero, what if one of the vectors was zero? You can't then conclude, but I still have a right angle, because you don't. If you have two vectors, but one of them's the zero vector, there is no angle, right? Angle between this vector and what? It's not pointing anywhere. It's not long enough to point. Right? So that's annoying. Right? So if you were to state this result without making the assumption of non-zero, what you'd really have to say is, if a dot product is zero, then here's a list of possibilities. One possibility is that one vector is zero. The other possibility is that the other vector is zero. Oh, I suppose it's also possible that they're both zero, or if none of those is true, then it's a right angle. Right? That's a lot. It's really inelegant. Right? So we get around that with this definition. I say get around it. I mean, we sort of we gloss over it with this definition. This word orthogonal. We say two vectors are orthogonal if and only if the dot product is zero. And then you leave it to the context. Right? If you say, dot product is zero, so boom, orthogonal, you just got to know what orthogonal means. Orthogonal means these three possibilities. Either one or the other of the vectors is zero, or neither is zero and you have a right angle. It's kind of a little convenient. Sweeping under the rug, I suppose you might say. Yeah.
What would a better way of thinking be? Would it be to check if it's orthogonal and then check if there's zero vectors?
It depends on what you want and what you know, right? So, situation, context will be your guide. What we're going to find actually pretty soon, not today, but next week, possibly even Monday, I'm not sure, is that sometimes whether or not you have a right angle might actually be less interesting than whether the dot product is zero. So in such a case, then who cares about the angle? I don't need to know the angle. I need to know if the dot product is zero. And then orthogonal is just, not only is it's not then sweeping ideas under the rug, it is going to exactly what you want. So every situation is different, and so I don't want to break down it. There's a million different possibilities, right? But these are what the two words mean, and you have to, just be careful with the relationship. Yep. Okay. Okay, so so real quick, here's a couple of vectors, non-zero vectors. We want to know if we have a right angle. And, well, that's arbitrated by, is the dot product 0? Yes, they are. Dot product is 0, so right angle. So perpendicular. And they're also orthogonal. Yeah. Okay. Alrighty. Okay, a couple of nice applications of the dot product I'm going to show you. The first one is to something called components. This is a reasonable thing to want to know sometimes. By the way, we're going to do a ton of stuff with components when we get into Chapter 15. Side note, in case you haven't heard the rumors, Chapter 15 is kind of what all of what we're doing in this course is building up to, is what we call vector calculus material that's in Chapter 15. So this is going to be a big deal in Chapter 15, this idea of a component. Sure. Another thing that I wanted to mention about this course. So there's 4 chapters that we're going to cover, 12, 13, 14, 15. We're going to flash back real quick to Chapter 10 at some point. So those 4 chapters, 12, 13, 14, 15, are not going to be equally represented on the final exam. Fair warning now. The proportions, the weights on the final exam are going to be 20, 20, 20, 40. So nearly half of the final exam is going to be on that Chapter 15 material. So there's a couple of reasons for this. One of the reasons is that, any question that you do with Chapter 15 is probably going to also use material from the earlier chapters anyway, right? So if we do 20, 20, 20, 40, it might actually kind of make it closer to working out pretty evenly, depending on how you look at it. The other thing is Chapter 15 is just really, really, really important. So one of our big clients in this course is the Pratt School. A lot of y'all are engineers, right? And the engineers have made it emphatically clear that Chapter 15 material, aka vector calculus, is the most important thing for y'all to get out of this course, right? So we don't want students we don't want there to be an under focus accordingly. Okay, anyway. Okay, so here's the idea of what a component is. Suppose you have a vector W, and you use that vector to define a direction. Let me see if I can do a better job there. Use that vector to define a direction. And the component then of another vector, if you have some vector V, the component of that vector says, all right, to what extent does my vector V actually point in the direction that I'm interested in, namely the direction defined by W, right? So if you interpret one vector as defining a direction and another vector, you want to know how much it points in that direction, that's what a component is. Again, it turns out this is a really useful idea. I mean, here's a silly example, but if football game, right? If somebody makes a lateral pass and then the receiver is tackled immediately, well, the ball may have flown 15 yards, but that's not a pickup of 15 yards. You did not just move the ball down the field. We're only interested in the extent to which the ball has moved downfield, right? So a lateral followed by a tackle is a gain of 0 in that direction because the ball went in that direction. It's only the component in the forward direction that we're actually interested in. Yeah.
Is projections?
These words get used in different ways in different contexts. I mean, I would like to think of a projection as being a vector, not a distance. But you're going to see in other contexts people will use projection the way I'm using component, and probably vice versa as well. But I'm just going to go with the book's choice here. Yeah. Right. Okay, so easy trig, as it turns out. Right, you look at this right triangle here. That's a right angle. And trig tells us that. And then you look at the right side of that equation, and you think, oh my gosh, that looks a lot like our existing formula for dot product, Right? Notice if I just multiply and divide by the magnitude of W, then all of a sudden my numerator looks exactly like my formula for dot product. And I can then replace all that cosine business with just a dot product. I've replaced, what on a calculator is advanced, scientific function with a really easy little formula that involves three-function arithmetic. Not even dividing. Dot product is just multiplying, adding, subtracting maybe through the minus sign. Right, so that's a nice simplification, and we got a cool, handy little formula for components. Nice thing that dot product does for us, it makes it really easy to compute components. So, like I say, this is going to come up pretty heavily in Chapter 15, so be on the lookout for that later in the semester. Now, a real quick side note, notice that if your vector here, the vector defining the direction, if that were a unit vector, then you'd be dividing by 1, which you could just toss. Right? In that special case that you're looking at a unit vector, components are just computed straight up with dot products. That's super useful. And this again is also going to come up really heavily in Chapter 15. It's a big deal. So in these situations where we're going to want to understand components, the way we're going to deal with our desire to have components is we're going to find unit vectors that point in that direction, because then we can compute these components just with a dot product. It's awesome. Okay. All right. Okay, moving along. Here's another application. Now, this is a physics thing, and if you haven't had physics before, no problem. We're going to do a little bit of physics in this class, just because the applications are really, really strong. But an easy formula from physics is for this thing called work. If you've not heard of work, no problem. Here's what it is. Work just says, and how you want to say it, how much effort does it take to accomplish a task? And the high school definition that gets written in high school physics classes is force times distance. And the idea is the harder you have to push, the more effort it takes to accomplish that task. The further you have to push it, the more effort that it takes, right? So work is a pretty natural choice, I think, of words here. And like I say, this is the old high school formula. Now, there's an asterisk with this formula. The asterisk on this formula is that's if the direction that the force is pointing, keep in mind force is a vector, is the same as the direction that you're actually pushing it, namely the displacement direction. And if they're not pointing in the same directions, then you have to replace force with component. And this is kind of annoying, but this force here, I'm not actually interested in the actual force vector or the magnitude of the actual force vector. I'm only interested in the extent to which it points in the direction I'm actually going. Right? So to whatever extent I'm pushing that way while I'm going that way, that's not really work. In fact, if I were clever, right, I would just kind of lean to the left. Kind of redo my balance, just kind of lean to the left and counteract that force that way. I'm not really working. If I'm just leaning, the wind's blowing me and I'm just kind of leaning in and just find a nice little happy medium, right? Along those same lines, if I want to roll something along the floor, well, there's a tremendous amount of force that way. That's gravity, right? But I'm going that way. And of course, I think y'all are easily persuaded that even a heavy bowling ball, it's really easy to roll it along the floor. Okay. So you have to look at the component of the force, not the actual force itself. So that being said, now recall that we have a formula for components. There's our formula for components. The distance that I'm traveling, right? How far am I going? Well, that distance is, it's the magnitude of the displacement vector. Those cancel. And we get this really, really nice formula that work is dot product. You might even say it's still kind of the case that work is force times distance, kind of, sort of times, right? But the big change is we're no longer viewing force and distance as being scalars. In fact, that was fundamentally a flaw in the original point of view. We already know forces are vectors. We already know displacements are vectors. Why are we writing them as scalars? And then talking about asterisk, well, and you got to look at the directions and the cosine and oh my gosh. Right? What an awkward and unnatural way to look at it. It's actually much more natural to recognize forces are vectors, displacements are vectors, and work relates to them by way of a dot product. End of story. No asterisk. Really convenient. Okay. So, plug and chug example. If you've got a force and a displacement, right? Work, force dot displacement. A little bit of arithmetic. Okay. All right, so that's it for dot products. Moving along to cross products and determinants. There's a bunch of stuff in this section. I'm going to go kind of fast through parts of this. Some of what I'm about to show you is supplemental, and it's there largely for context and kind of, I don't know, filling in the story a little bit. Side note, I'm going to be doing this material in an order that is significantly different from the order that the book does it in. It's a personal choice. I like my way better, right? But anyway, so you're going to notice those differences. Keep that in mind when you're looking through the book. I'm going to start off with something that's here kind of for context, and seemingly a silly question. Suppose I have a couple of vectors, like these, right? There's a couple of vectors. Here's those same two vectors, just I want to talk about them twice, so I'm going to write them twice. If I were to think about an order that I put on that list of vectors, so I could think of this one as being first and that one as being second. That's an order. On the other hand, I could call that one the first one, I suppose, and I could call that one the second one. So forget about the vectors themselves. If I want to distinguish these orders from each other, how would I? What would be a natural way to distinguish between those orders? And there's different choices that you could make. One thing you could say is, well, did I go in alphabetical order or not in alphabetical order? Suppose these vectors had names. Okay, well, yeah, but that's not really talking about the vectors. That's talking about the meaningless labels that I put on them, right? So you could talk about, well, maybe we go left to right, right? So maybe I kind of feel like this is sort of left to right because, the first vector is slightly further to the left, whereas this one's right to left because the first vector there is slightly to the right. But you can see that's perspective dependent. I mean, how silly is this? If I turn my head just slightly, then that changes, right? So that's not very satisfying. So here's what I think is a really good answer, and it's clockwise, counterclockwise. Whichever vector you put first, whichever one is 1, let that define a direction, and then which way gets you to the direction of the second vector most immediately. And so this is what I would call counterclockwise, because from my first vector, I rotate counterclockwise to get to the second vector. And I guess you could go around the other way, but the shortest direction, counterclockwise. Whereas, on the other hand, if I were to put that one first, right, that defines that direction. Which way do I go to get to the second vector? I go clockwise. Okay. All right. Who cares? It's a long story. We're going to get there. Okay, analogous question. What if you have, instead of 2 vectors in 2 dimensions, what if you have 3 vectors in 3 dimensions? Is there kind of a notion of clockwise, counterclockwise in 3 dimensions? And and it's subtle and it's subtle. So I'm just going to show you the answer. It's called right-hand order, and these pictures are really hard to draw, so I'm going to hand wave literally. So here's the definition of right-hand order. Let's suppose I've got a couple of vectors. There's the first vector. There's the second vector. And then the third vector I'm going to say is that way, let's just say. Okay, so 1, 2, 3. Right? Okay, here's the rule for right-hand order. Take your index finger, point your index finger parallel to your palm, and no hand yoga, just point the index finger the way that the index finger wants to go, parallel to the palm. Right? Like little bang bang. Okay. Point your index finger in the direction of that first vector. All right. Now, next thing, your middle finger. Notice your middle finger wants to bend a certain way. Again, no hand yoga, please. Don't. You could bend your middle finger like that, but let's don't. Okay, but bend it the way it wants to bend. Right? Okay. How are you going to get your middle finger to point in the direction of that second vector? Now, here's the thing. I mean, if I'm pointing my index finger in the direction of the first vector, notice you do have some flexibility still with how you sort of orient your hand. Notice my index finger is still pointing in that same one direction. Right? So, figure out what you got to do to orient your hand such that when you bend your middle finger, you can get your middle finger pointing in the direction of that second vector. Right, remember, first vector, second vector. All right, so I don't hold your index finger like this because now I can't get my middle finger to point that way. Right, so you got to rotate it around as necessary to get your middle finger to go toward the direction of the second vector. Okay, your thumb of your right hand then points on a well-defined side of the plane, right? So you look at the plane defined by the first two vectors, first vector, second vector, that defines a plane. Your thumb, in this case, it points on what you're going to maybe call the top side of the plane, right? But notice it could be the bottom side if your first vector was like that and your second vector was like that. So don't think of it as top and bottom. Don't think about left and right. Don't think about forward, back, right? First vector, second vector, your thumb will point in the direction of what we call the right hand side. I'm going to call that the right hand side of the plane. It's right in the sense that it's the thumb of your right hand. Okay. So if your third vector points in the same direction as your thumb, and by same direction I mean just on the same side of the plane as your thumb, then we say that list is in right hand order. That's my definition. So here's a couple observations that you can make, and I think these are kind of neato. Right hand order and left hand order are mirror images of each other, just like clockwise and counterclockwise are mirror images of each other. How about that? Right. So this really is a lot like clockwise, counterclockwise. This is kind of a three-dimensional version of clockwise, counterclockwise. There's two different possible choices, and they are mirror images, just like clockwise, counterclockwise. So I think that's cool. A couple other neat things about right-hand order and left-hand order. If you, I'm going to call this cycling. If you cycle a list of vectors, that preserves the handedness. So here's what I mean by that. Let's suppose ABC is, it doesn't even matter. Maybe it's right order, maybe it's left order. If you take the first vector and just kind of pick it up and move it around to the end, make it the last vector. That's what I'm going to call cycling. Then this next order is the same. So if ABC is a right-hand order, BCA is also a right-hand order. And I'm going to show you a very quick hand-wavy demonstration, plausibility argument of this. You can think it through. We don't have time to talk through in class, but here's the demonstration right there. Everybody see what I'm doing with my hand there? So, right, see what I have here, this is the demonstration of right-hand order on a list of vectors where that's the first one, that's the second one, and that's the third one. This is a demonstration of right-hand order of the same three vectors, just ordered differently. Now that's the first one, that's the second one, that's the third one. So you can think through the geometry and persuade yourself, this is what cycling looks like geometrically. And you can see pretty clearly that if you start with a right-hand order, you're going to be left with a right-hand order. And likewise, if you start with a left-hand order, you're going to end up with a left-hand order. That's kind of a neat point of view. Okay. So these are always the same, and these are always the same. Oh, and let me use a different color for that. And so not only are these the same and those the same, it is further true that these are always opposites of each other. If ABC is a right-hand order, then BAC is a left-hand order, and vice versa. That's kind of cool. Okay. Likewise, if you trade two vectors, if you just switch the positions of B and C, that's not a cycling, right? That's a different kind of a change of the order. Trading always changes the order. So if ABC is a left order, then ACB is a right order. And again, we don't have to, but this is kind of, I can't get my hands my hands are made out of stuff, unfortunately, and so I can't get them to superimpose exactly. But roughly speaking, this is the argument there. Two vectors, you switch the order, right? What was a right-hand order becomes a left-hand order. Okay. All right. Okay, I just wanted you all to see what that is. We're now going to go on and define something called a determinant. I think most of you all have seen determinants before, at least in some form. Here we go, determinant of a 2x2 matrix. AD minus BC, flashbacks to Algebra 2, maybe? I'm not sure when they include that in high school. Most high school curricula include it somewhere, though. Some neat things you can do with determinants. Makes comments about solutions to systems of equations. Y'all remember like simultaneous equations and stuff? And this tells you like, if this is 0, you have a problem, roughly speaking. Right? So you may or may not have seen the formula for the 3x3 determinant. Here's that formula. It's a weird one. It's weird. I'm sorry. But here's the idea. You go along the top row, and you look at those elements. A1, A2, A3. For each one of those elements, you're going to cross out the row and the column that it's in. You're going to look at the remaining 2x2 matrix, and you're going to take the determinant of that 2x2 matrix. That's the first term. And then you keep going all the way across that top row. So next term in the top row, A2. Cross out its row and column, and what remains are these 4 elements, making a 2x2 matrix like that, which you take the determinant, etc. And the one additional little detail, give me 2 seconds. The one additional detail is that as you go across the top, you have to alternate the signs. It's really hard to motivate why that is. Ultimately, why that is a deep fact. It's well beyond what we could reasonably talk about in this course. Nevertheless, it has to be there. So don't forget to do that alternating, and specifically as you're going across the top row, don't forget about that minus sign. A lot of students forget that minus sign and get a wrong answer. Yeah.
I was going to ask why.
Oh yeah. Sadly, it's deep water. Yeah.
When would you learn that?
You might learn it in Math 221, maybe. Possibly not. Sorry?
No, we don't do that.
You did not?
No.
Okay, all right. It depends on who's teaching it. When I taught 221, I did, but even the way I presented it was like I kind of scratched the surface of it a little bit. But if you were to take a more advanced algebra class, maybe like an abstract algebra, I don't even know if 401 would do it. It might be more of a 501 thing, 502. Yeah.
So is this? So over here we have like plus, minus, plus, right?
Yeah.
Is the order the same if we go to the middle row?
No. So you'll notice here now I'm only defining determinant here with specifically as we go along the top row. Now some of y'all might know additional facts about determinants, right? So there is a version of this formula where if you modify it appropriately, you're allowed to pick any row you want, or even any column that you want. It's very strange, right? And if that's the case, then it's not always plus minus plus. It's what it is a checkerboard pattern of pluses and minuses, and why that is Math 221 at least. Yeah. Yeah. It's a weird formula. Oh yeah.
Does the minus have anything to do with the fact that if you wrote it as B3
C3, B1, C1, sort of going.
Yeah.
If you wrote it like that,
Well,
the other determinant, it would be a plus.
I mean that. So the thing is, I kind of have to write this way if I want to preserve the order that these things are written down here.
Right to left, going
Yeah.
to the columns.
No, yeah. But I mean, what I'm pointing to though is, how come I can't just make this a plus right here? That's what I'd like to ask. Why can't it be a plus with these written as they are? And you're quite right. I could switch them and then make a plus. But then, I mean, as written here, as suggested by the initial layout, why is there a minus is a hard question.
Think of it as going like,
You can hide that minus somewhere else.
what I'm saying is it's like sort of moving in the right direction. Like if you start with the column to the right of the.
Well, then why is that true, though? I mean, ultimately, yeah. So there's deep water here, unavoidably, right? And so what I'm trying to get across is that I don't want to pick at that particular scab because it's big. It's really hard to get to a good answer. And ultimately, kind of the answer is we have a minus sign here because if we don't, it doesn't end up being a very interesting formula. It's kind of like that formula for dot product. Why did we choose the formula for the dot product the way we did? Because look at the cool geometry that comes out if we do. Right? So it's ultimately that, but why the minus sign gives that cool geometry to you is deep water. Yeah. Okay, so here's the first little cool geometry fact I want to show you. There's a couple of them I'm going to show you today, but here's the first one. It takes a while to write this down, so bear with me. Suppose you have a couple of vectors, a first vector and a second vector, in that order. The order matters. Remember the whole clockwise, counterclockwise thing. So this is not just a set of vectors. This is an ordered list of vectors. A is first. B is second. On purpose. Okay. Now I'm going to do two things with that list of vectors. The first thing I'm going to do is I'm going to make a matrix out of that list of vectors by just making those coordinates the rows. Now, I can make anything I want, right? I'm going to make a matrix like that. It seems like a plausible, I don't know, not clear why, but this is not the craziest thing we've ever seen. The next thing I'm going to do is I'm going to take those two vectors, write them geometrically in the plane. We are in R2, after all. And I'm going to define a parallelogram with them. So notice, I've created, on my own will, all right, I've created this algebraic thing called a matrix, and I've created this geometric thing called a parallelogram. I didn't have to do any of that, but I'm just saying, hey, free country, I want to do this. Right? So I've made these things, and now I claim that determinant connects these things in an unbelievable way, as follows. The absolute value of the determinant will tell you the area of that parallelogram. Isn't that mysterious? And furthermore, the sign, plus or minus, of that determinant will tell you whether it's clockwise or counterclockwise as listed. So determinant, even though determinant's defined, let's see here, determinant is defined algebraically, what we're seeing is that it has some shocking geometric interpretations. Determinant's magnitude tells you about the area, and its sign tells you about the order. An area and order are geometric concepts. Okay, and I'm not going to prove these facts. I'm just going to claim them. There's different ways to prove this fact. You can do some really hairy algebra / trig and prove this fact. I don't really see the point of that. The best way to prove this, in my opinion, is to use some sophisticated tools that are a little much for Math 221, but I guess you can do it. I did it. But those really sophisticated ideas prove this result in a much nicer way. But it's sophisticated and it's not Math 212 appropriate. So I'm just going to, rather than show you a proof that's unnecessarily complicated or a proof that's inappropriately deep, I'm just going to claim that this is true. Okay. All right. Yeah. So here's the three possibilities. Determinants either positive or negative or zero. That tells you about order, clockwise, counterclockwise, clockwise, or neither. and it tells you about area as well. Okay, so that's why this wacky little formula is interesting geometrically. And there's an analogous fact. Let me just squeeze in this last little thing here. There's an analogous fact if you have 3 vectors. So let's suppose you have 3 vectors in R3, A, B, A, B, C. You can write them algebraically or geometrically. Right? And amazing result, the determinant, its absolute value tells you the volume of that parallelepiped, and the sign, plus or minus, tells you handedness, namely right-hand order, left-hand order, or neither. So this is another way, how it connects to determinant is another way in which that whole right-hand order thing is highly analogous to clockwise, counterclockwise, and that kind of thing. And it's another example of how determinant, this wacky formula with the weird minus sign in it, right? This wacky formula with the weird minus sign is geometrically natural along the lines of volume. What is more geometrically natural than volume? Okay, all right. Call it a day. See y'all later. Have a good one. Have a good weekend.